Hi everyone. I hope you all enjoyed the talk I gave last week on Lagrange interpolation polynomials, where we discussed how the Lagrange method is used to construct and interpolating a polynomial, right, that fits given sets of data points. While it's powerful techniques, one of its limitation can be computational complexity when dealing with larger sets of data. Today we are fortunate to have Pitamar Acharya with us, who will be giving us a detailed presentation on Newton interpolation polynomials. And this method is another essential approach to polynomial interpolation. It offers significant computational advantages, particularly when adding new data points to an existing set. So Mr. Acharya is a research student at University of Alabama at Birmingham, United States. He will take us through the theory and applications of Newton's method, showing us how it can be more efficient in certain scenarios compared to Lagrange approach. Okay, so without further ado, please join me in welcoming Mr. Acharya.
The topic of my talk is about the Newton interpolation formula, and particularly I'll discuss more about the divided difference method used in Newton interpolation formula. Uh, so I'll be discussing the brief of interpolating data, and then something about interpolating functions, and then I'll go to the Newton interpolation polynomial, and then the divided difference. So interpolating data. So we are given a collection of data samples, xi, comma yi. There are n samples. So the xi are known as the abscissa, and yr are the data values. So our aim is to find a one function vx, which can be used to estimate the sample function for distinct values of x. Sometimes we call this distinct value x as nodes. So interpolation is to estimate the values Vxi, which is equal to the data values Yi. So why it is essential? Because discrete data often comes from sensor or computation, but we need information as if the function were sampled continuously. We need to plot, we need to differentiate and integrate the data trend. To obtain an economical approximation for the data, we need interpolation. So what are the interpolating functions? A function fx may be given on the interval. It is a bounded interval a comma b, which is either explicitly or implicitly. Then we seek an interpolant vx such that the functional value at xi v is equal to the functional value of xi at f. And that point xi lies in between a comma b. The same algorithm used for the interpolating data can be applied here. However, in this case, we may be able to choose the abscissa and estimate the interpolation error. Yeah. So interpolation formulation, for the interpolation formulation, we have many ways to define a function, Vx. So sometimes we use polynomial function, trigonometric function, exponential function, a rational function, sometimes wavelets, curvelets, rislets, or sometimes radial basis function. Then there are many more functions to define the interpolation polynomials. So let's consider a linear combination of linearly independent basis function. We call this as phi j x. So this is Vx can be written as the linear combination of phi jx, where this coefficient Cj are the interpolation coefficient, or sometimes they call interpolation weights. So this is the linear form. This is the linear combination of basis function. So we can compute this combination in terms of matrix. So we separate the coefficient, the weight, the C0, C1 in this column, and then the value of the estimates Y0, Y1 on the right hand side, and this big matrix is the matrix of the basis functions. So this matrix I'll call is A, C equals Y. Now, this linear equation will become a matrix equation AC equals Y. The special case here, the function phi 0x, phi 1x, up to phi nx, they form a basis for all the polynomials of degree at most n. And this type of basis function holds the simplest and basic form of interpolation. It is used as a building block for other methods, including interpolation, integration, and the solution of differential equations. So our goal here is to learn the methods for polynomial interpolation. Let me digress to the linear equation. Uh, there are something to uh, be familiar with what the condition number is. So we have a linear system Ax equals B, where A is a matrix, and X and B are the column matrix. Due to approximation error, we have a slight perturbation by delta A. So let's call that delta A plus delta A by A cap. Similar in the solution, there is a perturbation delta X. So we call X cap equals X plus delta X. So we have B equals A cap X because B is unchanged, A cap X cap. So we replace this A cap by A plus delta A. That means we have AX cap plus delta X cap, which implies that this is B minus AX cap equals delta A X cap. So we have this delta X, the slight difference, the slight change equals X cap minus X. So this is identity matrix. So we can write A inverse A X cap for X cap minus, and this X can be replaced from here. It is A inverse B. So ultimately we have negative A inverse delta A X cap. So if we take norm on both sides, norm represents the magnitude of this matrix. So norm on both sides, so delta X is less than or equal to uh, norm of A inverse, norm of delta A, norm of X cap. So we should remember that while using the norm, this equality will be changed by inequality. This is the property of norm, matrix norm. So if we divide both sides by if we divide both sides by X cap, then we'll get this value. The first delta X divided by X, then the output is less than or equal to the norm of A inverse multiplied by norm of A, and then that quantity multiplied by delta A over A. So the left hand side is the relative output error, and the right hand side is the product of two things. The first one is the norm of A inverse and the norm of A, that's the product. And the second one is relative input error. So there is a slight change in A that will give the change in X. So this uh, A inverse, the norm of A inverse and the norm of A, when we take the product of these two quantities, we'll get a number. That number is known as the condition number. So perturbation on B also have the similar effect. So overall, the result is roughly this relation. Delta X over X is less than or equal to condition number of A multiplied by this quantity. So why is this important? Because while we change a simple amount in the input, so there will be the change in output. So sudden change in input sometimes give a rapid change, a big change in the output, and sometimes small changes in input will give the small changes in output. So if the change is big, we call the matrix the ill matrix, ill conditioned matrix. Otherwise, if it is good, then it is called well conditioned matrix. Okay, let me go to the basis function again. So if we construct a basis function phi jx as x to the power j, then this construction of basis is known as the monomial basis. This is the simple construction in case of polynomial interpolation. Now the polynomial will become P and X or Vx, this is equal to the sum of Cj x to the j, where Cj are the coefficients that ranges from j equals 0 to n. Similarly, we have another polynomial function, that is a polynomial interpolation function, which is constructed by using Lagrangian basis. So now phi jx can be replaced by Ljx, which is given by this product formula. The product of the fraction between x minus xi and xj minus xi. This Lagrange basis phi jxi is defined as 0 when I is not equal to j, and this is equal to 1 when these two indices are equal. So ultimately, the Lagrange polynomial function will be px equals the sum of yj multiplied by this phi jx, which will be replaced by this interpolating, the Lagrange basis given here by phi jx. So I'm not going to discuss more about the uh, basis regarding monomial and Lagrange. So my aim here is to discuss more about the Newton form. So what actually the basis for the Newton form? The motivation is we need to introduce the interpolation data xi, yi, one period at a time, rather than all at once from the start. The estimating error in the interpolating approximation. The monomial basis is given by x to the power j. So this monomial basis is simple in case of uh, uh, monomial interpolation, but the matrix is dense. The matrix is solved by using LU decomposition, which is comparatively more expensive. The matrix is a Vandermonde non-singular matrix. So there is a uniqueness. So there is a precisely one interpolating polynomial. But the bad part is the worst part of this matrix is it is ill-conditioned increasingly as we increase the degree of the polynomial. It means that the value of the coefficient are poorly determined. The computational complexity is more. The construction cost is in the order of n cube flops. The evaluation cost is, if we use harder method, then it is in the order of n flops. So potential stability difficulties if degree is large, the FC size spread out. So there are a lot of drawbacks in case of monomial basis. Similarly, in case of Lagrange polynomial basis given by this relation, the construction stays easy. It is not as simple as monomial basis. However, the matrix A constructed that I showed earlier, this is let me go here. Yeah, this is the matrix. This matrix A, the matrix consisting of the basis, is an identity matrix. The coefficients are immediately determined here. Here, the construction cost is in the order of n square flops. The evaluation cost for each x is in the order of n flops. It is stable if the degree is large or the abscissa spread apart. So while comparing with the monomial basis, it is also more difficult to differentiate. It is more difficult to integrate. So Lagrange polynomial interpolate is easy to determine, but more expensive to evaluate for a given argument compared with monomial basis interpolation. So in case of monomial basis interpolation, we can uh, we can differentiate it easily, but in case of Lagrange polynomial, it is difficult. So there comes Newton polynomial basis. Newton's polynomial basis can be viewed as a useful compromise. The basis function is given by this relation. So the matrix A that we defined earlier, it leads to a lower triangular matrix. So neutral interpolation has a better balance between cost of computing interpolant and cost of evaluating it. So here's an example. For a quadratic interpolant, we have phi 0x. This is equal to 1. Phi 1x is given as the difference of x and x naught. And phi 2x is given as the product of these two factors, x minus x0 and x minus x1. So to evaluate C0, we only need the first data points. To evaluate C1, we only need the first 2 points. Similarly, to evaluate C2, we only need first 3 points and so on. Here is example. Suppose I have a data 2, 14, 6, 24, 4, 25, 7, 15 here. I have this 4 points. So by using Newton basis, the basis function phi 0x is equal to 1, phi 1x is equal to x minus 2 by using this formula, and then phi 2x is equal to this one. Phi 3x is the factor of these three quantities, x minus 2, x minus 6, x minus 4. So we can construct a matrix like this one. We can see that the diagonal elements are 1, 4, negative 4, positive 50. Sorry. So it is a lower triangular matrix. If C is a matrix of the coefficient, then we can easily solve S equals Y. So the matrix of coefficient is given here. It is a column vector with the elements 14, 2.5, negative 1.5, and negative 0.2667. So here comes the divided difference. Actually, the Newton polynomial interpolation takes the form this one. P and x is equal to C0 plus C1 multiplied by x minus x0 plus C2, which is the coefficient, x minus x0, x minus x1. Similarly, Cn is the coefficient, and we have factors like this one, x minus x0, x minus x1, x minus x, and minus 1. So Newton, in case of Newton polynomial interpolation, we have the alternative method called divided difference, which is useful in determining the coefficients. It is used more often than solving a linear system. It makes easier to add the points. We can add more points and we can delete the data points. So in this case, divided difference will helps a lot. Divided difference have an interesting connection with function derivatives, and it provides a tool with which we'll analyze the interpolation error. So how can we represent the divided difference? So let me explain here. The Newton polynomial is given by this relation. Suppose yi equals f of xi, then the coefficients c0, c1, c2, cn that can be determined as follow. So let's find the coefficient c0. So if we plug here x0 and this expression, the Newton polynomial expression, then we can get the elements or the terms apart from c0. All these values are 0 because we plug here x0, x0 minus x0 becomes 0. So ultimately we get c0 equals f x0. When we plug c1 in this polynomial interpolant, then Pn Cx, Pn xn equals fx1, fx1. The rest will become 0. So C1 is given by Pnx minus C0 divided by x minus x0. So we can replace C0 by fx0. So we'll get this slope-like formula. It is actually a slope. Similarly, to determine C2, we plug x equals x2 in the polynomial interpolant. And by computation, we get the value of C2 equals this expression. So continue this process until all Cj are found. The coefficients Cj are known as the zth divided difference, and this is denoted by f bracket of x0, x1 up to xj. So this is the notation for zth divided difference. So here Cj is the zth divided difference coefficient. We denote this by f of x0, x1 up to xj. So in terms of divided difference notation, we represent C0 by F bracket X0. We did denote C1 by F bracket X0, comma X1, C2 by X0, comma X1, comma X2, and so on. Now, the Newton divided difference interpolation formula will be like this one. Just replacing C0, we get the formula, this one. Fx0 plus Fx0, comma X1, X minus X0. So compactly, we can write this in this product form like this one. So we have a recursive formula for the divided difference. F of x0, x1, x2 up to xj. This is given by the difference of f from x1 up to xj and x0 up to xj minus 1. So we divide this whole quantity by xj minus x0. So divided difference are defined recursively by this relation. So if we start from xi and go up to xj, then the numerator will be the difference of these two quantities. Start from xi plus 1 and it will go up to xj. The second quantity here, the abscissa will start from xi and then they will go up to xj minus 1. So the involved here, the quantities are from xi up to xj. So we subtract them, these two quantities, the topmost and then the bottom one. The coefficient for the Newton interpolant are just Cj given by this one. The diagonal elements in the table, I'll come back to the table later. So to add another data point, so if we have n data, but we want to add another one data point, then the data will be, there are n plus 1 data. Then we can use the divided difference and construct a table like this one. The first column is the value of I. So how many data we have? There are n plus 1 data. So xi, this is the value of f theta, x0, x1, x2 up to n. So we have the functional value of xi. So the fourth column will give the divided difference. So here, this remains vacant, this remains vacant. So we have values only on the diagonal. So in the first diagonal, this we have fx0 here, and second, fx1 minus fx0 divided by x1 minus x0. And this one, fx0, fx1, fx2. And ultimately, we have the value of a divided difference, f of x0, and it goes up to xn. The diagonal entries yield the coefficient Cj, where j start from 0 and ends at n. So this is all about divided difference table. So an example will illustrate in detail. So suppose we have four data points, negative 1, comma 1, 0, comma 1, 1, comma 2, 2, comma 0. So to determine the interpolating cubic polynomial by using uh, the divided difference table, we construct this table like this one. So first, in the first column here, we write the values of xi, negative 1, 0, 1, 2. And in the second column, we have yi's, 1, 1, 2, 0. So this first remains in the third column, we have no calculation for the first row. So it starts along the diagonal. So 0, we use the formula for the divided difference. So this is 1 minus 1 divided by 1 minus 1 will be 0. So this is the quantity we get. So this will be our C1, and this 1 will be the C0. So we ultimately construct the value fx0, the coefficient fx0, x1, the coefficient fx0, x1, x2. These are nothing, just C0, C1, C2, C3, because we are constructing the cubic polynomial. So substituting the value of C0, C1, C2 in the Newton polynomial, we'll get the Newton polynomial interpolant as Px equals 1 plus 7 over x, 6x plus 1 over 2x squared minus 2 over 3x cubed. So we can compare these three basis function. So in case of monomial function, we have x to the power j. The construction cost is in the order of n cube. The evaluation cost is in the order of n. So it is simple. So in case of Lagrangian polynomial interpolation, the basis function is a complex function like this one. Here also the construction cost is in the order of n square. The evaluation cost is in the order of n. So it is the most stable. However, in case of Newton basis, we have the construction cost in the order of n square, similar to the Lagrange. The evaluation cost is also similar to all these tools, but it is adaptive. Adaptive in the sense that it is a sequential construction. It can be adjusted dynamically. So the advantage of Newton polynomial interpolant is that it is easier to evaluate than Lagrange polynomial. Also, when we add a new data point, it is very easy to handle because the computation processes one step at a time. Thank you very much. And these are the references. Any questions?
All right, thank you very much. Thank you for this wonderful presentation. Um, I was just curious. You said the importance of the divided difference, right? So the important in constructing of the Newton interpolation polynomial. So what actually are the divided difference in Newton polynomial compared with the Lagrange polynomial?
Yeah, because the first step is the Lagrange polynomial interpolant is complicated. So
Mhm.
it is complicated in the sense that it is difficult to differentiate, it is difficult to integrate, and there are many more things like that. And while constructing the Lagrange interpolation polynomial, you need all the information. And if you want to add another point, then you need information from the beginning. So you need complex calculation. But in case of divided difference, you can see the table. If you want to add one other point, let's say here is 2 comma 0 is the fourth point, you can add 5 comma 6, another one point. Then you don't need the previous information. Sorry, you don't need all the previous information, just one step ahead. You can use the information one step ahead. So the computation process is very easy. So people frequently use Newton interpolation method and the divided difference table. So when data points are given, and if you are given to choose in a given period of time, so the Newton interpolation formula is the better one, and the divided difference table will be simpler to calculate.